Section 3.2 is about conditional probability and the multiplication rule. So let's talk about conditional probability. Conditional probability is the probability that a second event or an event will occur given that another event has already occurred. So there's different notation for conditional probability. We still use P for probability, and then we use this vertical line. So this is notation for the probability of B happening given that A happened already or happened first. So we're going to first start off using an example that we have a table. So what we have over here, we'll do this one first. 2 cards are selected in sequence from a standard deck of 52 playing cards. Find the probability that the second card is a queen given that the first card is a king, assuming that the king is not replaced. So the notation that we'd be using for number 1 is the probability that we draw a queen given that a king has already been drawn. So the probability that we draw a queen would be the number of ways that we can get a queen knowing that we already drew a king. So there's 4 queens starting out in the deck, and we want the probability that we draw a queen, so there would still be 4 queens in the deck because we drew a king. So then assuming that we drew a king the first time, then how many possible outcomes are there when we draw the card? Well, there's normally 52 cards in a deck, but we've already drawn a king, so now there are 51 cards in the deck. So the probability that we draw a queen the second time, given that we drew a king the first time, would be 4 out of 51. On the second one, now we'll use this table. The table at the left shows the result of a study in which researchers examined a child's IQ. So we had either a high IQ or a normal IQ, and then looked to see if a specific gene was present or not present. We want to find the probability that a child has a high IQ, given that the child has the gene. Okay. So in order to figure out this probability, we need to know the probability for having a high IQ knowing that the gene was already present. So we know the gene is present, which means that we're only dealing with these possible outcomes over here because the gene is already present. So we are kind of narrowing our sample space down to the gene being present. So given that the gene is present, the number of outcomes for high IQ is 33. And the total number of outcomes is only 72 because we know the gene is present. So it would be 33 out of 72, which would simplify to 11/24. Okay, let's look at another example, another problem using that same data. The try it yourself. We'll label that number 3. Refer to the study in the second part of example 1 over here. Find the probability that, they have 2 parts for us. 1, a child does not have the gene. So the probability that the gene is not present. Now, that is not a conditional probability. That's just a regular probability, an experimental probability. So that would be the number of outcomes where the gene is not present. So the gene is not present in, I can scoot that down. The gene is not present 30 times out of the total number of outcomes, which is 102. So the gene is not present 30 out of 102 times, which would be 15 out of 51 or 5/17, I believe. Then in part 2, they want to know what is the probability that the child does not have the gene, so the gene is not present, given that the child has a normal IQ. So now the number of outcomes where the gene is not present is not 30, because we're already working on the assumption that they have a normal IQ. So we're only looking at the normal IQ. So the gene is not present in 11 of those individuals. So there's 11 outcomes where the gene is not present out of 50 total that have a normal IQ. So that probability would be 11 out of 50. In order to be able to move forward and work with some of our other probability concepts, we need to understand the difference between dependent events and independent events. So dependent events would be when we have a series of different events happening in which the outcome of the first event affects or changes the probability of the second event, versus independent events where the outcome of the first event does not affect the probability of the second event. So if I am drawing cards out of a deck and I put the first card back before I draw the second card, then it's like resetting the problem. So if I'm drawing a card and I put the card back, then the first event does not affect the probability of the second event. So this would be, for example, drawing cards, and we call that with replacement, because I'm replacing that card. However, if I draw the first card and I don't put it back, like my queen and king example, if I draw the first card and I don't put it back, then what happens the second time is going to have a different probability than it would have the first time. So this would be like drawing cards without replacement. So I keep the first card out when I draw the second card. When your events are independent, in other words, the probability of the first thing doesn't affect the probability of the second, then the probability of event B happening, given that event A has happened, since A doesn't affect B, then that would be just equal to the probability of B happening. That is because the first event, which was A, does not affect the second event, which is B. So for independent events, the probability of B occurring, given that A already has occurred, is equal to the probability of B. So let's make some decisions about events being dependent or independent. In number 1, we are going to select a king, event A, from a standard deck of 52 playing cards, not replacing it, and then selecting a queen, B, from the deck. So right in there it says not replacing, and without replacement is going to change the probability. So these are dependent events. tossing a coin and getting a head, and then rolling a six-sided die and obtaining a 6. So if I first toss that coin and then roll a 6, will the outcome of the coin event have an effect or change the probability on rolling that die? No, it will not. So these are independent events. How about driving over 85 miles per hour and then getting in a car accident? So if I first am driving over 85 miles per hour, do you think that that will change the probability that I get in a car accident? Well, let's see. The probability that I get in an accident, given that I'm going over 85 miles per hour. I'm going to say that these are dependent. And the reason I'm going to say they're dependent is because the probability of being in an accident changes based on your driving speed. Okay. Next, smoking a pack of cigarettes a day and developing emphysema, which is a chronic lung disease. So the probability that you get emphysema given that you smoke 2 packs a day. Those are going to be dependent. For sure, if you smoke 2 packs a day, the risk of getting emphysema is going to be higher. How about number 2 down here? The probability of getting a heads on the dice, then tossing a coin and getting the tail. I've got this backwards. So the probability of getting a tail, given that the first thing I did was toss heads on the dice. On the coin. So since a coin just has the 2 sides and each side is equally likely, it doesn't matter what I got the first time, which was heads. The second time is independent of the first time. In fact, even if I got heads like 10 times in a row when I tossed the coin, I would still have the same chance of getting tails on the 11th time. Now that we've talked about independent and dependent events, let's get on to the multiplication rule. The multiplication rule deals with the probability of 2 events occurring in a sequence. In sequence is. So the notation for that is the probability of A and B. So rolling a 7 and getting tails on a coin. So probability of A and B is equal to the probability of A times the probability of B, given that A has already occurred. Now, what we just saw a second ago is that if the events are independent, then the probability of B occurring given that A has occurred is just equal to the probability of B occurring. So that gives us this new formula for independent events. The probability of A and B occurring would just be equal to the probability of A occurring times the probability of B occurring. And then this formula can be extended to any number of events, as long as they're independent. So any number of independent events. So when we see the word and we're dealing with probabilities, we should be thinking in terms of multiplying. So let's look at some examples. 2 cards are selected without replacement from a standard deck of 52 playing cards. Find the probability of selecting a king and then selecting a queen. So we want the probability of selecting a king and then selecting a queen. So that would be equal to the probability of selecting a king times the probability of selecting a queen, given that we selected a king already. Now, without replacement means that these events are dependent. So I don't get to use the simplified formula. So when I work this through, this is going to be equal to the probability of getting a king the first time would be 4 out of 52. And then on the second draw, since I already drew a king, the probability of drawing a queen would be the 4 queens out of the 51 remaining cards, which is 4 out of 663. Because when I simplify 16 out of 2652, that's what I get, 4 out of 663, or approximately 0.006. In number 2, we have a coin that is tossed and a die is rolled. Find the probability of tossing a head and then rolling a 6. So probability of a head and a 6. Now, when I'm rolling dice and tossing coins, these are independent events. So when I find this probability of heads times the probability of 6, given that we rolled a heads on the coin, would be equal to the probability of tossing a head on the coin and then multiplying by the probability of rolling a 6, since they're independent. So probability of the first event is 1/2 times the probability of the second event, which is 1/6, gives me 1/12, which is approximately 0.083. Try it yourself. The probability that a salmon swims successfully through a dam is 0.85. The probability that 2 salmon, we want to find the probability that 2 salmon swim successfully through the dam. So the probability that the first salmon is successful, we'll say S1 for successful salmon 1, and the second salmon is successful. So it's telling me the probability is 0.85. So these 2 events are going to be independent, because whether or not the first salmon makes it doesn't have any effect on the second one. So this will be the probability that salmon 1 is successful times the probability that salmon 2 is successful. So that would be 0.85 times 0.85, which is approximately 0.723 using our rounding rule. Try it yourself, number 2. 2 cards are selected from a deck of 52 playing cards without replacement. Find the probability that they are both hearts. So the probability that I draw a heart the first time and I draw a heart the second time. These are going to be dependent because I'm doing this without replacement. So when I find these probabilities, this will be the probability that I get a heart the first time times the probability that I get a heart the second time, given that I got a heart the first time. So the probability of getting a heart the first time, there are 13 hearts in a deck and there are 52 playing cards. So I need to multiply that by the probability that I get a heart the second time, given that I already drew a heart. So if I already drew a heart the first time, then that means there's not 13 left in there. There's only 12 left in there. And since I already drew a card the first time, there's not 52 left in the deck. There's only 51. So when I multiply that, 13 divided by 52 times 12 divided by 51, that gives me approximately 0.059, which is 1/17. Let's do some more practice using the multiplication rule to find probabilities. For ACL reconstructive surgery, the probability that a surgery is successful is 0.95. So we want to find the probability that 3 ACL surgeries are successful. So in other words, we're finding the probability that the first one is a success and the second one is a success and the third one is a success. Since these are going to be independent, like think about, 3 people go in for surgery, what happens to the first person is not going to have any effect on what happens to the second person, and same thing with the third person. So this will be equal to the probability of the first success times the probability of the second success times the probability of the third success, which was 0.95 times 0.95 times 0.95. So that will be 0.857375 or 0.857 for our round off rule. On the second one, we're going to find the probability that none of the 3 surgeries are successful. So this is also going to be independent. So now we're looking at, I'm going to put this down in here, the probability that the first one fails and the second one fails and the third one fails. Since those are independent, that will be the probability that 1 fails times the probability that 2 fails times the probability that 3 fails, which will be, since the probability of success is 0.95, the probability of failure is 0.05. So 0.05 times 0.05 times 0.05, which is 0.000125. If I round that to 3 decimal places, that is a 0% chance of all 3 failing. If I didn't round it, then it would be a 0.01% chance of failing, 0.0125. So not very likely to happen. Find the probability that at least one of the surgeries is successful. Okay, so we're going to talk about complementary events here, because here is my sample space. My sample space is having, I have 3 surgeries. So what I want to find is the probability that at least one is successful. So that would include the possibilities of 1 success or 2 successes or 3 successes. So out of the 3 surgeries, that only leaves 1 possibility out here in the complement, and that is 0 successes. So the probability based on complementary events. So complementary events. The probability of having at least one success plus the probability of having 0 success is going to be equal to 1. Well, the probability of having 0 successes we just figured out was 0.000125. And then what we want is the probability of at least 1 success. When I add those together, I get 1. So I can solve this and figure out that the probability of getting at least 1 success will be 1 minus 0.000125, which is 0.999875. I think we'll skip these, try it yourself, because it's basically the same problems that we just did with the ACL surgery. And we'll go on to using the multiplication rule to find probabilities. About 16,500 U.S. medical school seniors applied to residency programs in 2012. 95% of the seniors were matched with residency positions. Of those, 81.6% were matched with one of their top 3 choices. So this just describes what happens is that medical students rank their residency programs in order of preference, and programs directors rank the students. And then matching means that's the process where a student's preference list and a program director's preference list overlap, resulting in placement of the student in a position. So this 95% of seniors were matched. I'm going to say that means that the probability of matching is 0.95. Then it goes on to tell us of those 95%, 81.6% were matched with one of their top 3 choices. So before you can get to the 81.6, like that's 81.6 of these people who were matched. So this is going to be the probability that you get your top 3 given that you were matched with someone, and that's going to equal the 0.816. Okay, so let's answer some of these questions. Find the probability randomly selected senior was matched with a residency position and it was one of the senior's top 3 choices. So we're looking at the probability that they match and it was a top 3. So based on our multiplication rule, that's going to be the probability that we get a match times the probability that it's a top 3 given that we got a match. Now, are these events independent or dependent? Well, since I can't get in my top 3 unless I already have a match, these are dependent. So when I calculate this probability, the probability of getting a match was 0.95. And the probability of being a top 3 school given that I got a match is 0.816. So all I need to do then is multiply those together. And that's going to be 0.7752. If I'm following the rounding rule, it would be 0.775. Now let's find number 2, the probability that a randomly selected senior who was matched with a residency position did not get matched with one of the senior's top 3 choices. So now we are looking at the probability that they were matched and did not get a top 3 choice. So this would be the probability of getting matched times the probability of not top 3 given that we matched. So these events, will they be dependent or independent? Since you can't be matched with a school, like you can't get one of your not top 3 if you're not matched in the first place. So these are dependent as well. So this will be equal to probability of getting matched is 0.95. Now we know the probability of getting a top 3 if we get a match already. So then the probability of getting a school that is not in your top 3, given that we got a match, would have to be all the rest of the people. So instead of the 81.6% that did get their top 3, there will be 18.4% who did not get a top 3. So that'll be 0.184 for that probability. So then we need 0.95 times 0.184, which would be 0.1748 or 0.175 by our round-off rule. Number 3 wants to know, would it be unusual for a randomly selected senior to be matched with a residency position and that it was one of their seniors' top 3 choices? So they're looking for the probability of getting matched and the top 3, which we've already figured out is 0.7752 or 77.5%. So remember that 77.5% of students get matched with one of their top 3 choices. Now remember our distribution here. And where those usual data fit within 3 standard deviations of the mean. So very unusual was more than 3 away. Unusual was more than 2 away. But it was in here within these 2 standard deviations from the mean. So remember, these 2 were each 34. These 2 were each 13.5. So that meant that 95% of our data would be in the usual range. So since 77.5 got matched and in our top 3, we would consider that to be not unusual. Okay. In a jury selection pool, 65% of the people are female. Of these 65%, 1 out of 4 works in a health field. So the probability that somebody in a jury selection pool is female would be 0.65. The probability that they work in a health field, given that they are female, would be 0.25 because it's 1 in 4. So we're going to look at some probabilities based on this. Find the probability that a randomly selected person from the jury pool is female and works in the health field. So this would be the probability that they are female times the probability that they work in the health field given that they are female. So that would be the 0.65 for the first event times the 0.25 for working in a health field given that they're female. So 0.65 times 0.25, that is 0.1625. Would this be considered unusual? No, not unusual. Because 95% of the data is usual, so that only leaves 5% to be unusual, which would be 0.25 or 2.5% down here, 2.5% at the top. Find the probability that a randomly selected person from the jury pool is female and does not work in a health-related field. So this is probability of female times probability of not working in the health field given that they are female. So probability they're female was still 0.65. And then the probability that they wouldn't work in the health field given that they're female would be the rest of them, which would be 75% of them, so 0.75, which is 0.4875, which is also not unusual.